Okay, so the last speaker of this session is going to be Jakob, and he's going to be telling us about how to improve bottom-up enumerative synthesis techniques. Take it away.
All right, so welcome to the presentation of our paper, Oriented Metrics for Bottom-up Enumerative Synthesis. And this is joint work with Roland Meyer, and I am Jakob Tepe. So the goal of today's talk is that we want to unify and generalize the existing approaches to bottom-up enumerative synthesis. So let's first talk about a problem that we can solve using bottom-up enumerative synthesis, which is syntax-guided synthesis, also called SYGUS. So in SYGUS, you're given a specification in the form of some examples, input and output examples. And these define the ground truth. And the ground truth transforms the inputs into their corresponding outputs. Then you're also given a grammar. And this grammar defines the search space of all the possible solutions. So the task now is to find a program inside that search space which implements the ground truth. Now let's look at a concrete problem instance. We have these input examples and these output examples. So we have to convert POPL''conf to POPL', REN_city to REN, PLDI_conf to PLDI, and SOL_city to SOL. And we are also given a grammar. And this grammar allows us to return the input variable x, the empty string epsilon, conf or city. We can use the replace operator, which I will explain later, and we can use concatenation, which is just the usual string concatenation. And our task now is to find a program inside the grammar that converts each input into its corresponding output. The solution to this problem is the following program. I will explain this in more detail right now. So the R is an abbreviation for replace, and we can check that this is a solution by plugging in the first input example. So if we evaluate the inner replace operation on POPL''conf, conf, and epsilon, we replace the conf part inside POPL''conf by the empty string epsilon. This essentially deletes the conf part, and we're just left with POPL'. Then, in the outer replacement, we replace the city part inside POPL' by the empty string. But since there is no city inside POPL', we are just left with POPL'. Now we can plug in the second example, REN_city. We do the inner replacement first again. We replace conf inside REN_city by the empty string. Since conf is not inside REN_city, no replacement happens. We still have REN_city. Then we do the outer replacement. We replace city inside REN_city by the empty string epsilon, which just deletes the city part. So we're left with REN. This works for the third and the fourth example in the same way, and so this is a solution to our problem. Now, how do programs come up with the solution automatically? And our first understanding is that existing approaches have a way to enumerate. So here we have our problem instance again, and bottom-up enumeration will start by enumerating the smallest programs which are inside the grammar. In our case, it's returning the input variable x, epsilon, conf, or city. So these are now the programs of size 1 in our current program pool. To generate new programs now, we use the operators, which are allowed in the grammar, to combine the programs we already have enumerated and get new programs from them. So if we apply this, we have no program of size 2, but at size 3 we can use the concatenation operator to get the programs x concatenated with x, x concatenated with epsilon, and so on. So every possible combination of the programs of size 1 using the concatenation operator. Now at size 4, we can use the replacement operator to generate new programs. At size 5, you have even more programs. At size 6, even more. And then at size 7, we eventually enumerate the solution that we've seen before. Now, as you can see, this has an exponential blow-up. Like, if we look at the sizes of the sets of programs, and if we don't use any smart method to shrink that size, then in the first program set of size 1, we have only 4 programs. At size 3, we have 16 programs. And at size 7, we already have more than 4,000 programs. And this is just for this simple grammar in this toy example here. Now, if we zoom a bit out and look at this more abstractly, we have our search space here, and somewhere in there is the ground truth. And we just enumerated the programs along some enumeration order. And what we did is we enumerated the ones of size 1, and then some bigger programs, so we enumerated them along their size. One trick you can do is use deduction, which was studied in various Cygers papers before. And what deduction does is the following. During the enumeration process, you've seen that we enumerated epsilon, city, then some more programs. At some point, we enumerated the program that replaces conference by the empty string. Then we enumerated some more. And at some point, we got to our solution. And now deduction realizes at this point, we have enumerated all the components of our solution. And it will just move up the solution in our enumeration order so that the solution is the successor of the last component needed to build the solution. So it's just a change in the enumeration order from this abstract point of view. Now the second thing that existing approaches do is they have a way to factorize the search space. Now, the first approach that was done towards this is the observational equivalence factorization, which was applied in 2013 to synthesis. And this states that 2 programs are observational equivalent if they behave the same on the given input examples. So program 1 and program 2 are equivalent if they have the same output on the given input examples. For example, the program X and the program X concatenated with epsilon will return the same output on the given inputs, and therefore they are equivalent. And this equivalence factorizes the search space. And we only need to keep 1 representative per equivalence class, and thus we can prune away many programs. For example, we have the program X and the program X concatenated with epsilon, and we only need to keep the program X. So X concatenated with epsilon can be thrown away. Now, if we apply this to the problem from before, then you can see that at size 7, instead of having more than 4,000 programs, we only have a bit more than 100 programs. So this has a significant impact on the search space. The next thing you can do is for factorization is abstraction. This was applied to synthesis in 2018, and the idea is to take the observational equivalence a step further. So instead of comparing the outputs, the concrete outputs of 2 programs, we first apply an abstraction function and compare the abstract output of these programs. So 2 programs are then equivalent if for each input their abstract output is the same. And this results in a coarser equivalence, and we still only need to keep 1 representative per class, and thus we have less programs to consider. Now, the second understanding is that existing approaches have a way to prune the search space. This was applied to synthesis in 2023, and the idea is to use a metric to define a ball around the ground truth. And then you only want to consider programs inside that ball. Now, this approach is deliberately incomplete. You might have pruned a program, so a subprogram of your solution is outside the ball, so you have pruned that, but you need this to build your solution. And if you've pruned the program, you can't build the solution anymore. But you can control this completeness or the speed up via the radius of the ball. So we can have this rather big radius, then we get more completeness, but less speed up. We can have this smaller radius, so we are more incomplete, but we have a bigger speed up because we consider less programs, or we can find some middle ground. One downside here is that metrics require symmetry, but I'll get to that point later. Now, to sum up, the existing approaches have a way to enumerate, they have a way to factorize, and they have a way to prune the search space. Now, we can capture the enumeration by the enumeration order, which is a total order on the search space. The factorization can be captured by the equivalence, and the pruning can be captured by the metric we use. So these are the three parameters of bottom-up enumerative synthesizers. And our insight now is that the equivalence and the metric can really be captured inside one object, an oriented metric. So instead of three parameters, the enumeration order, equivalence, and metric, we only have two parameters, the enumeration order and the oriented metric. So now, what is an oriented metric? An oriented metric is a function that assigns a distance between two objects. And it has three properties. The first one is reflexivity. So from object A to object A, we should have the distance 0. The second one is that we are symmetric at 0. So if we have the distance from B to A of 0, then the distance of A to B should also be 0. The last thing we have is the triangle inequality. Now let's focus on this middle part here, the symmetry at 0. This allows us to be asymmetric. We only need to be symmetric at 0, but everywhere else we can allow for asymmetry. And we will see later that this results in better pruning. It also induces an equivalence. So with this we can express observational equivalence factorization and abstraction. So why do we want this asymmetry? The answer is that many Cygos operators, they exhibit asymmetric behavior. Let's look at a few examples. So we have the concatenation operator for strings, for example, and symmetry would require that the distance from the string POPL to the string PO is the same as the other way around, from PO to POPL. Now the concatenation operator, however, only works in one way, in one direction. It always produces superstrings of its inputs. Since POPL is a superstring of PO, we cannot produce PO using concat and POPL. But the other way around, since PO is a substring of POPL, it might help us produce POPL using the concatenation operator. So if we design a metric for the concatenation operator, we would like to have a big distance from POPL to PO, because concatenation doesn't help producing PO from POPL, but a rather small distance from PO to POPL, because with concatenation, we can go from PO to POPL. The next example is replacements with epsilon. So again, symmetry requires that from POPL to PO is the same way as the other way around. But the replace operator also only works in one way if the epsilon is the last parameter. So then we only get substrings of the first parameter. Now, since POPL is a superstring of PO, POPL might help us produce PO using the replace operator. But again, the other way around, PO is a substring of POPL. In this case, PO cannot produce POPL using the replacement with epsilon. Now, here we also want to have a small distance from POPL to PO, because we can go from POPL to PO using the replacement operator. But the other way around, we might want to have a big distance from PO to POPL. Now let's switch domains to the bitvector domain and look at the bitwise AND operation. So symmetry would require that the distance between the bitvector 110 to 100 is the same as the other way around, from 100 to 110. But the AND operation also only works in one direction. It always produces bit vectors which are bitwise less than its inputs. So since 110 is bitwise greater than 100, 110 might help us produce 100 using the AND operation. But the other way around, 100 is bitwise less than 110, and thus 100 cannot produce 110 using the AND operation. And again, we might want to have an asymmetric metric here. So we want to have a small distance from 110 to 100, but a big distance from 100 to 110. And that's why we want asymmetry. So the next point is the equivalence. Now, an metric induces an equivalence at distance 0. So two objects, A and B, are equivalent if their distance is 0. We can quickly check that this indeed is an equivalence. So we get the reflexivity property from the reflexivity of the metric. We get the symmetry property from the symmetry at 0. And transitivity follows from the triangle inequality. And with this, we can express the observational equivalence factorization and abstraction methods from before. So how can we design such an metric? And the answer is that we first construct an metric on the data domain, and then we can lift that one up to programs. So let's design an oriented metric for the replacement operator. The idea is that we want to reward superstrings of the outputs. So for two strings, I and O, we assign their distance from I to O as the difference in length if I is a superstring of O. But if I is not a superstring of O, we get a penalty of 100, and then we take the difference in length. Let's look at a few examples. So from PO to POPL, we now have a distance of 102. Since PO is not a superstring of POPL, we get the penalty of 100, and the difference in length is 2. The other way around, from POPL to PO, we have a distance of 2, because POPL is a superstring of PO, and the difference in length is just 2. So we have this asymmetry here, and also the intuition from before, as we discussed the replacement operator. Because we can go from POPL to PO using the replacement with epsilon, we have a rather small distance, but the other way around, we can't go, so we have a big distance. So now we want to lift this up for two programs, P and Q. And what we do is we evaluate the programs on the given input examples and then measure the distance there. So the distance from P to Q is P and Q evaluated on the input examples and the distance is summed up. Now let's apply this to the example from the beginning. We have the search space again, and we set the radius of our ball to 100. And now we might encounter a program like city concatenated with city. And we want to check, is it inside the ball? So we measure the distance to the ground truth. Now city.city always evaluates to city, city. The ground truth executed on the input examples will return the output examples, because this is the specification of the ground truth, right? So the ground truth will output POPL, REN, PLDI, and SOL. And since city, city is not a superstring of POPL, REN, PLDI, and SOL, the distance to the ground truth is greater than 100. And thus, we might prune this program. Now, if we apply this pruning and check the sizes of the program sets, then the last program set of size 7, instead of having 4,000 programs, we are only left with 900 programs. So we can prune quite a bit. Now, we can apply the factorization, and we factorize the search space by the induced equivalence of the metric. And this is the same as the observational equivalence factorization. And now combining these two approaches, we're only left with 81 programs inside the last set. All right, now we've packed this whole thing into a framework, which is parametric in the two parameters from before, the enumeration order and the orimetric. And as input, we have the grammar and the ground truth. And what we do is we first prune and then factorize the search space. Then we enumerate alongside our enumeration order. And then we might wind up with a program P, which is the correct solution. What I haven't shown you today is how to use abstraction with the orimetrics. Then you might want to introduce refinement. And if you have a previous loop, a previous enumeration process, then you can learn from that previous enumeration process and get a different enumeration order. But for this, you have to read the paper. Now, in practice, we will instantiate this algorithm using concurrent instances employing different orimetrics. So we might have orimetrics tailored towards multiple operators. And we implemented this in a tool called Merlin and evaluated it on the Cygas benchmarks. So on the bitvector domain, we are 25 times faster than dry instance, which is the next best tool on the bitvector domain. On the string benchmarks, we are competitive with the Synthonia string solver. Then we also compared against Blaze, which can also solve strings, and we are 75 times faster than Blaze. And against the baseline implementation, which does not use the pruning and does not use the learning, but you haven't seen that part, we are 42 times faster than the baseline. So to conclude, you have seen a framework for bottom-up enumerative synthesis, which is parametric in the enumeration order and the orimetric. Then you've seen oriented metrics, which have the three properties, reflexivity, symmetry at zero, and the triangle inequality. And lastly, you have seen that implementing these has a substantial impact on performance. Thank you for your attention.
Raise your hands if you have a question.
Thank you for good speech. And my question is, what is exactly you learn? And like some constraints, like always be the superstring or substring, or the parameter like 100. What is the learning parameter?
Okay, the learning is, in practice, we say we have found a partial solution to the program in like the abstract space. And then with that solution, which works in the abstract, we will take the orimetric and evaluate this solution for all the examples, so in the concrete space. So then you have this abstract solution, and we check if it's feasible or if it's a good solution in the concrete space. If so, we will enumerate it very early in the next iteration. So what we do is we change the enumeration order.
Could you say a bit more about how the interaction between two different or multiple orimetrics works? So you presented them, depending on which operator you use, you prefer one metric or the other metric. So if I have a program that needs to use two operators with different, that have the flipped asymmetry, how would you do that?
Yeah, that's a good question. And currently, we are not very smart about it. So we just run different instances with different orimetrics concurrently. And we don't care if we have, for example, the concatenation and the replacement operator inside the grammar. We just have one instance which runs with the orimetric tailored towards concatenation, and one instance with the orimetric tailored towards replacements. But this is future work.
Okay, thank you. Do you see a way to combine that, or having a more tailored orimetric that switches depending on what the next operator is considered in the enumeration?
At the top of my head, I don't know how to change the orimetric on the fly, but maybe that's a good angle to look at. Thanks.
Okay, thank you.
Hi, thanks for the talk. So you deliberately give up the search completeness, right? To my understanding,
Yes.
you confine the search to a fixed radius. Is it fair to compare your tool against the other tools that guarantees the search completeness?
Well, so in practice, our tool is also complete because we also run one metric, which is very trivial and which doesn't result in any pruning. So we have that as kind of a backup. But yeah, it's a fair point. Maybe it's not too fair to compare again complete tools. I don't know about that, but fair comment, at least, I think.
All right. And you cannot apply oriented metrics for operators which are symmetric, right? Do I understand correctly? For example, addition is...
Addition would also,
addition
like,
operator, yeah.
If it's on the bit vectors, then you have a problem because you kind of can wrap around with the overflow, so you don't know where to come from.
Yeah.
If you would be on the integers, you would always know that you need less values. Like, if I need to reach this integer, I can only get from lesser values. But with the overflow, it kind of corrupts that intuition, right? So we currently don't have an metric for the add operator.
Okay, yeah. And the last question is, can you find any insight that can be reused for defining oriented metrics for any new underlying operators in your paper?
Can you repeat the question?
Yeah, I mean, how much difficulty should we expect for defining oriented metrics for new underlying operators rather than Cygos operators?
Okay, so currently we only give an intuition in the paper, which is more than we gave in the talk. So having a streamlined way to do it is future work for us. The idea is to kind of try to measure the inverse semantics. So if you have a bit vector, which is very close to the solution and bitwise greater than the solution, then there are many other bit vectors with which you can use the AND operator to get the solution. But you might also have a bit vector which is, again, bitwise greater, but not so close to the solution, so more bits are different. Then there's only fewer other bit vectors which you can use the AND operator with to get the solution. So that's our intuition to kind of measure the inverse semantics. But we haven't done anything formal about this till now.
I see. Thank you.
Let's thank the speaker one last time.